Welcome to the Math 1, Unit 8, Lesson 1 summary video, Quanika's Quilts. This is a develop understanding task, which is meant to introduce you to a concept but not necessarily finalize rules or strategies. The purpose of this lesson is to understand equivalent expressions obtained from factoring trinomials with only positive terms using rectangular area models. In this task, Quanika is a quilt maker who has set up a booth at the North Carolina State Fair where children can design their own quilts of varying dimensions. We're going to be using area models to develop the understanding of equivalent expressions obtained from factoring trinomials. I'm going to be using algebra tiles in this video, but you may also draw the area models if you don't have access to tiles. Each of these area models will begin with a square block of fabric with side length x inches. We know that the area of this block will be x squared, and you can see the tile that I have on the board now, and so its dimensions are x by x, which gives us an area of x squared. Some of the children want to create rectangular blocks instead of a square block by extending the side lengths of x. For example, we can start with the square block and extend one side by 5 inches and the other side by 2 inches. Now keep in mind, we want to end up with a rectangular block. So we're going to look at how we can use an area model to fill this in. So again, we're starting with this square block that's got side lengths of x and an area of x squared, and we're going to extend this one side out by 5. So we're going to add 5 units, or inches. We're using inches, so we're going to add 5 inches to the one side. So when we added those 5 inches, this piece right here of the square again is x units long. We're adding 5 inches, which makes each of these pieces 1 inch. We know that this side is x units long, and properties of a square, we know that opposite sides of a square are congruent, which makes this side of the square also x units long. So if this side is x units long of this rectangle that we added on, and the top portion of it is 1 inch long, in order to find the area, we multiply that length by the width, or 1 times x, and we get an area of x. And so we did that for each of these. On the other side, we extended this side, this x width or length, on this side by 2 inches. And so this is what it looks like when we add those on. And it's the same theory for finding the area of each of these rectangles. We know that this side length would be x, and each of these lengths would be 1. So it's x times 1 to give me an area of x in each of those. Now, as we already discussed, we need this to be a rectangle. It's a quilt. So we're trying to complete and fill in this entire rectangle. We know that if this side length right here is 1, this side length is also 1. And we know that if this side length is 1, this side length is also 1. So in order to fill in the area where they match, where they meet up, that we're going to put a 1 block here, and it's going to have an area of 1 because its dimensions are 1 by 1. And we're going to repeat that for each of these. And so if we look at what we originally started with, we know that in order to find the area, we have to multiply the length times the width. And so when we were just looking at the square, we were saying the area of x is x squared. But now we've taken each side length of x and changed it. So now for the length, we've got x plus 5, and for the width, we've got x plus 2. And so the combined area, if we count all of these tiles up, we've got an x squared here, and we've got 1, 2, 3, 4, 5, 6, 7 x's, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so what we can see is that this expression is equivalent to this trinomial expression. And just to prove that these are equivalent, we're going to look at how we can get from the first expression mathematically to the second expression. And we'll do that using the distributive property. So if I distribute each of the first terms, or if I distribute the first term in the first binomial to the first term in the second binomial, I get x times x, which is x squared. Then if I distribute that first term in the first binomial to the second term in the second binomial, I have x times 2, which is 2x. Now, if I distribute the second term in the first binomial to the first term in the second binomial, I get 5x. And if I distribute that the second term in the first binomial to the second term in the second binomial, I get 10. 5 times 2 is 10. Now I can combine my like terms in order to simplify, and I get x squared plus 7x plus 10. We're going to look at another example where we are starting with our original square quilt of x by x, and this time we're just going to add 2 to one side. So we're not going to add anything to the other side, and we can see what this looks like. If we add 2 in, this is what it looks like in our model. And so what I end up with is the expression, I've got x times x plus 2. And if I look at my area model, I've got 1x squared and 2 x's. And if we use that distributive property to distribute this x to each of the terms inside the parentheses, x times x gives us x squared, x times 2 gives us 2x. So these are just two equivalent expressions that can be used to represent this model. In this example, we're given this expression here, and we're asked to create the area model and describe what the rectangle would look like, and then write an additional expression representing the area model. So we can see that here's the order for the new quilt. They want it to have 1x squared, and so we have that here. They want us to have 2 x's extending out on one side, and 3 x's extending out on the other side. And then we're going to have 6 1's, which will complete our rectangle. And we can simplify this by combining our like terms. We can also count up our area model to see what we have. So we've got 1x squared, and then we've got 1, 2, 3, 4, 5 x's. So we've got our x squared plus 5 x's, and you can see that we can get those 5 x's by combining these like terms as well. And we've got 6 1's. So this example is similar to the last example, except now all of our x terms are simplified, so they're combined already. And so what we've got to figure out is how many of the x's are going to extend this one dimension and how many are going to extend the other dimension. And so what I know is I have 1x squared, I have 6 x's, and then I have 5 1's. And so if I think back to the other examples that we've done, we've started out with our square unit, and then we've added rectangles on to each dimension. And then this space in here is what we've filled up with our single units, our 1's. And so we know that these have to make a rectangle when we add our 1's in. And so when I look at the fact that I have 5 1's, there's no way for me to make a rectangle like this. So I can't do a 3 by 2. I would need 6 of them. And same thing if I move this one over here, a 2 by 3. So the only option I have, I can't put 4 on one side and 1 on the other. So the only option I have is to have all 5 of them together. And so what we know is that I couldn't put 4 on one side and 2 on another to get my 6 x's, because I wouldn't have enough 1's to fill all of this up. It would look like that. And so I don't have a complete rectangle. And if I were to put 3 on one side and 3 on the other, again, I still don't have enough 1's to fill this entire rectangle. But if I put 4 on one side, excuse me, 5 on one side and 1 on the other, now I can complete the rectangle by filling in this space with the 5 1's. And so what that looks like, the equivalent expression, we've got an x here, and then we've got 1, 2, 3, 4, 5. So we extended this side length out by 5, and on this side we have an x, and we extended this side length out by 1 inch. And so the expression on this side is x plus 5, and the expression on this side is x plus 1. And to check and make sure that we have it correct, we can distribute each of these terms in the first binomial to each of the terms in the second binomial. So if I distribute my x to my x and my x to my 1, I get x times x, which is x squared, x times 1, which is x. And now if I distribute the 5 to each of these terms in the second binomial, I get 5 times x, which is 5x, plus 5 times 1, which is 5. And now I'm going to simplify by combining my like terms, and I have x squared plus, this is 1x plus 5x, which is 6x, plus 5. And you can see that that matches our original expression.